Welcome back to this course on principles of polymer synthesis. We have been talking about the synthesis of polyurethanes in the last class, and we will continue talking about that in today's class also. So, the topic remains the same, synthesis of industrial polymers. So, we will directly go back to what we were discussing in the previous class, that was the spandex fibers. So, if you go to the structures now, so basically your diol you could react with a diisocyanate, and then you have your pre-polymer, and then you can react with your chain extender. In this case you are reacting with a diamine. Okay. So, in fact, this structure is not completely correct. Of course, you can figure out, because previously I have already given you the principle of how to draw the structures. So, I am going to redraw the structure here. So, let me draw it up again. So, you have now produced your NCO, NHCO, O. So, this is your pre-polymer. Now, this pre-polymer you are reacting with hydrazine, which is your chain extender. So, basically what you have to do is the following: you have your polymer chain. So, you start from this side and you have NHR. Now, this NCO will react with amine, all right, because that NCO here was missing. So, that was the mistake. So, you have to, when you are doing this, you have to do it very carefully, and you have to look at all the atoms that you are reacting. So, this NCO will react with NH2. So, that will be your NHCO. So, in fact, let me draw the carbonyl on this side, because I am drawing all the carbonyls at the bottom, it does not matter. So, NHCO, and then you have this amine. So, this will be NH, and then again you have to react on this side the amine with an isocyanate. So, then again it will be NH, all right, and then you are drawing up the rest of the molecule R, NH, N. So, this structure is correct. Actually, here what this isocyanate, the reaction of isocyanate with the amine, that particular part was not drawn here. So, this structure is your correct structure. So, basically what you will have here then is your urea linkage, and you will have the urea linkage here, and you have the isocyanate, you have the urethane linkage here. So, this is your hard block, and this is your soft block, all right, and your R is this. In this case, this is methylene diphenyl diisocyanate that you are reacting. Now, the polymers that you have prepared by this process, say you either you talk about a polymer which is based on a chain extender using a diol, or you can use a chain extender which is a diamine. In this case, a specific diamine we are using. So, what you will have is, in both the cases you will have a soft segment which is your flexible segment, which is generated from your macroglycol unit, and you have a hard segment which has a possibility of lot of hydrogen bonding interactions, all right, between your urethane linkages if you are reacting with a diol, or your amide linkages if you are reacting with a diamine. So, this is your hard block and this is your soft block. So, for the hard block the Tg is well above room temperature. For the soft block the Tg will be low. So, this soft block will be rubbery in nature, and this hard block, you know, so this will provide the material with the strength. So, we will discuss it in more detail now. So, what you do, let us say you have a melt of this material and you cool this down. So, what happens, this hard block and soft block, they do not mix very well. So, they have a low miscibility. So, they have low miscibility of hard and soft blocks, that leads to segregation. So, when you cool down the melt, what happens, the hard blocks and soft blocks, they do not mix and they segregate. So, basically they will what we call as micro phase separate. So, basically you will get a two phase system. So, you have a two phase system. Now, the domains that are formed by this hard block, what will happen is that those domains will be crystalline, because they are neatly held by these strong hydrogen bonding interactions. So, you will have a crystalline domains, and those domains will basically provide 3D cross-link centers for the whole material. Cross-linking is because of the hydrogen bonding interactions, all right. And those domains, or the domains formed by the hard segments, those will be responsible for the tensile strength of the material and for the stiffness of the material, all right. So, if you look at the situation a little bit more closely, so what will happen when you cool the system down? So, you have these kind of domains that will appear. I am just drawing it in a very simplified way. Now, these domains are basically your this part, your polyurethane, this segment. So, let me say each rod that I am drawing is basically this particular block, and the other, say this rod is from one polymer chain, this rod is from another polymer chain, this rod is from another polymer chain, and so, and these flexible units that you are having from each polymer chain, those are basically your macroglycol, that polyester part. So, you see that for each rod here I am drawing on both sides this kind of flexible chains, and then of course, at the end of this flexible chain you can have maybe another rod, and then again you have this kind of stuff, because you basically have a hard domain and a soft domain, and then this polymer molecule, you have a hard domain and then a soft domain on this side, again another hard domain, another soft domain, like this. The point is that the hard domains will come together through hydrogen bonding interactions. So, they basically provide 3D cross-link centers for the whole system, and these cross-links are basically present in the material, which will have a what you call as a soft matrix, which is made of these flexible chains, which are basically your polyester part, all right. So, obviously, then you have this kind of cross links, and these cross links will basically give you the stiffness of the material, and this will also give you the tensile strength of the material. But when you heat this material up, the interaction between the different chains, the hard blocks in the domain, that interaction will disappear, because the interaction is basically a hydrogen bonding interaction, which is reversible. So, if you heat it up, the material becomes processable. That is why it is a thermoplastic material, because if you heat it up, it will start to flow, and if you cool it down, then again these crystalline domains will appear. These are your crystalline domains, those crystalline domains will appear, and they will provide this kind of cross-linking interactions, and they will give you the stiffness and the strength of the material. What about the term elastomer? If you are looking at these flexible chains, actually this drawing becomes more complicated after, because in each domain, for each rod you will have all these flexible chains on both sides. After the flexible chain you will have another hard segment, so on and so forth. So, this material, if you look at this material in a closer detail, you have these soft segments that are protruding out of these hard blocks. Now, these soft segments, they are coiled sometimes like this, or they are wavy like this. So, what you can do when you are extending this material, until these soft domains are extended to their full length, you could continue to extend. So, they will break. So, what will be the breaking point at which all these flexible chains they become straight. So, basically you can say that these flexible chains contain hidden length. So, they can be extended. So, from there your stretchability will come, because your material is stretchable. Your material is not only stretchable, but your material is also having quite high stiffness because of this kind of appearance of this kind of crystalline domains of hydrogen bonding interactions between the hard polyurethane segments, and the material is also thermoplastic because these interactions will disappear, these domains will disappear when you heat it, and the material is also elastomeric because what happens is that they are stretchable, because you have all these soft flexible chains which can be extended to their complete length. Until they are extended to their complete length, you can keep stretching, and when you remove your applied force, applied outside force, they can come back, because I mean they do not start to flow when you keep applying force, because ultimately what happens is that these soft blocks, they are covalently bonded to the hard blocks. So, they just do not go away. So, the flowability of the material is restricted because the soft block is connected to the hard block, and when you release your applied stress, what will happen is that it can come back to its original situation. So, it will have this kind of stretchability, and of course, the material will have elasticity because it can come back. Whatever chains you have, if you stretch them completely and then if you release them, now these chains are not going anywhere, they are connected to these hard blocks. So, then they can again come back to their curly, this kind of situation when you remove the applied force. So, what will happen is that the material will also have elasticity. It will be non-linear, of course, because your stress versus strain is not linear after, but it will still be elastic. That is why it is called thermoplastic elastomeric material, and as I have already told before that the spandex has use in your fabric, in your clothes, especially for sports wear. You will co-spin this particular fiber with your nylons or with your polyesters. So, this also will go into the fabric, that will give the stretchable property to the material that can withstand a lot more wear and tear. All right. So, I think that is more or less that all that I wanted to talk about polyurethanes, but one of the other uses also is as foams, because those materials typically what can happen is that the carbon dioxide can evolve when you break these urethane linkages, and if you suitably process the material, this carbon dioxide can create a lot of volume inside the material, and then you can have what you call as foamy material. And this kind of thermoplastic foams, they can be used in automobiles, the interior of the automobile, they can be used in the dashboards of the automobile, or they can be used to make up the seats also. So, those are some of the uses that you should keep in mind. Okay. So, this finishes our discussion on thermoplastic polyurethanes in particular and polyurethanes in general. So, we talked about the synthesis of polyurethanes, specifically we talked about the thermoplastic elastomeric nature of the polyurethanes, how you can create hard blocks and soft blocks, how the hard blocks can come together when you cool down the melt and you create the crystalline zones or the hard domains that gives you the 3D cross linking points of the whole matrix, and that provides the stiffness to the material, and how those interactions will break when you heat the material up and then you get your thermoplastic material. And when you try to stretch the material, they can be stretched to 6 times or even 7 times like that. So, 600% strain, for example, the spandex fibers to 6 times the length they can be extended, and that is because they have all these flexible chains that can be extended to their complete length. I mean, they also contain the hidden length, as I am telling you, and they are also attached to your hard blocks. So, they do not just go away. So, if you remove the applied force, they can come back. So, that elasticity also is ingrained into the material, elastic property is also ingrained in the material. And last but not the least, this thermoplastic property, if you look at the thermoplastic property and if you somehow create some covalent crosslinks in the material, then that will destroy the thermoplastic properties. Why I am talking about covalent crosslinks is because if you remember in the last class we talked about the biurate and allophonate crosslinks, like your isocyanate can react with your urea linkage or it can react with your polyurethane linkage, both are present in the system, because in this case you are using, say for a spandex you are using a diamine, specifically hydrazine as the chain extender. So, what can happen is that these kind of crosslinks can form, and once these crosslinks are formed they are covalent. So, what do you think, that they should then destroy the thermoplastic nature because covalent bonds. But the point here is that these crosslinks are reversible, I already talked about it before. So, when you heat the material up, these crosslinks will break. So, the material becomes flowy again. So, even though such crosslinks like allophonate or biurate, such crosslinks can form in the material, they will break when you heat the material up. Of course, you have to heat the material in order to get the flowy nature or the processability out of it, the very definition of thermoplastic. So, the thermoplastic property is not destroyed. The bottom line is that this property is not destroyed despite the presence of this kind of crosslinks. All right. So, that finishes our discussion on urethanes. What we will start talking about next is epoxy resins. So, epoxy resins, they are typically characterized by the presence of more than one 3-membered rings, and those rings are typically epoxy rings, or you can call them as epoxide rings or oxyrene. So, typically those are epoxide rings like this 3-membered ring with an oxygen in it, this is your epoxide, and just putting different groups here. So, epoxy resins are typically characterized, as I told, by the presence of more than one such linkage, and these epoxy linkages can be opened up, and if you have a nucleophile that attacks here, it can open up here like that. So, you can cross link chemically a material which has this kind of linkages, you open up and then cross link, and that is called your curing, and ultimately what you can get are thermoset materials, which have permanent cross links which cannot be further processed by heating, and typically these are amorphous thermoset materials, and they will have excellent mechanical strength and toughness, good adhesive properties, so on and so forth, good corrosion resistance. Now, that is why typically you will use these as in protective coating applications, and this is a 3-membered ring and an oxygen is present. So, this is a highly strained system, So, that is why they can react with a wide variety of curing agents under diverse conditions, under diverse conditions or diverse temperature, different temperatures. So, that is what imparts versatility to this epoxide linkages, because ultimately you are going to get thermosets by opening up these epoxides and preparing cross-linking different chains, and these are highly strained, as I have already told, and wide variety of reactants, wide variety of cross-linkers or curing agents you can use. When you discuss the synthesis of epoxy resins, you start with what you call as liquid epoxy resin or LER. which is based on this molecule. This is diglycidyl ether of bisphenol A. So, the abbreviation is diglycidyl ether of bisphenol A, DGEBA. So, your liquid epoxy resins are typically based on DGEBA. We will explain why. Now, a little bit more about the name. So, if you have an alcohol on both sides, this is your bisphenol A. We already talked about bisphenol A. So, basically you start with phenol, which is your phenyl ring, and then OH. You react your phenol with acetone. If you react your phenol with acetone, then a condensation reaction occurs and you get your bisphenol A, OH on both sides. Now, diglycidyl ether linkage is basically this. So, this is diglycidyl ether. Okay. So, you see that unit is there on this side and this side, that is why it is diglycidyl ether of bisphenol A. All right. So, the synthesis of liquid epoxy resin is done by the following scheme. So, you react what you call as epichlorohydrin, you react your epichlorohydrin with bisphenol A, you react epichlorohydrin with bisphenol A, this is bisphenol A, in presence of sodium hydroxide, and then the product that you will get has the formula like this. So, this is your bisphenol A unit here. You have a secondary alcohol inside. And that ends with the glycidyl ether. So, basically if you look at this particular molecule, this is the general formula of the product, this is oxygen, this is the general formula of the product. So, you can see that if this N is 0, then basically what you have got is your diglycidyl ether of bisphenol A, on this side glycidyl ether, this side glycidyl ether, and then you have bisphenol A. So, if this is not there, then you have your bisphenol A and on both sides glycidyl ether. So, basically this is DGEBA, but if you have, so it all depends on the ratio between the two. If you have an excess of this, typically it is 10:1, then what will happen, this N value will be very close to 0, mostly you will have DGEBA or diglycidyl ether of bisphenol A, but when this proportion of this starts to become lower, less than 10:1, so this is 10:1, if it is less than 10:1, then this N value also will start to rise. As you can see that one more unit of bisphenol A has come inside here. So, of course, if the ratio changes, then this N, so this is the general formula. So, this N also, the value of this N also will change. So, we will discuss this in little more detail now. So, this will be your, so this is the general reaction for epoxy resins. Now, this will be your liquid epoxy resin when the degree of polymerization, which is your N, it is very low, N is very close to 0.2. That is why we told that a liquid epoxy resin is based on your diglycidyl ether of bisphenol A. This value is very, very low. So, this is typically mostly diglycidyl ether of bisphenol A. Now, as you can see already and you can suspect that typical commercial liquid resins or liquid epoxy resins, they are viscous liquids. They are viscous liquids, the n value is very small and their what you call as epoxy equivalent weight, their epoxy equivalent weight is around 188. What is this epoxy equivalent weight? What is this term that I have introduced here? Epoxy equivalent weight, the definition is something like this. This is the weight of resin required to obtain one equivalent of epoxy functional group. All right. So, let us say, so if you see for example diglyceryl ether, so one molecule has 2 epoxy units. Okay. If you look at this molecule, let us say n value is very high, still this one molecule has 2 epoxy units. But if you compare with this, of course this molecular weight is lower than this molecular weight. So, which of these two molecules will have higher epoxy equivalent weight? This molecule will have higher epoxy equivalent weight, because this is the weight of resin required to obtain one equivalent of epoxy functional group. So, if you take say the molecular weight is x, so if you then take x gram of this molecule, then you will get 2 equivalent. So, one equivalent of this molecule is basically your x gram of molecule is basically your molecular weight is x, let us say. In that case it is x gram will give you 2 equivalent. So, how many grams will give you 1 equivalent? That will be x divided by 2. So, that will be your epoxy equivalent weight. But if you look at here, this will also be say y divided by 2 if y is your molecular weight, but the molecular weight is lower. So, the epoxy equivalent weight here is lower. So, this is the definition then, weight of the resin required to obtain one equivalent of epoxy functional group. So, since the molecular weight is lower, in order to obtain one equivalent you will require lower amount of this. So, basically it is like how much is the proportion of the epoxy units present in the molecule. In a nutshell, this is the concept that is being provided by epoxy equivalent weight. If this epoxy equivalent weight is high, that means the proportion of the available epoxy units is lower in the molecule, because with respect to the molecular weight, if you have a very high molecular weight, then also one equivalent of the molecule is providing 2 equivalent of epoxy units, and if you have a small molecular weight, then also it is providing 2 epoxy units. So, of course, if you have a small molecular weight, the proportion of the epoxy units is higher. So, that is what is given by this epoxy equivalent weight. So, then the percentage of epoxide present in the material is basically 43.05 divided by epoxy equivalent weight into 100. So, of course, if your epoxy equivalent weight is higher, then your percentage of epoxide is lower. So, if your n value is higher, then your epoxy equivalent weight becomes lower. And what is 43.02? So, if you just take the epoxide here, so carbon is 12, hydrogen is 2 plus 2 4, oxygen is 16. So, this is 12 into 2, 24, it's close to 44. Actually, it is not that, because the there will be some decimal points, 20, so it will be 12 point something. Hydrogen is basically 1 into 4. So, this is 1 point something, and oxygen will be 15 point something, like that. So, this is basically your 43.05, close to that will be your molecular weight of this particular unit. So, that divided by epoxy equivalent weight is your percentage epoxide. Why you require to know this? Because when you are curing your epoxide resin, you need to know how much of curing agent you have to use. That is why you need to know what is the proportion of epoxy present in that particular molecule, and that is what is given by your epoxy equivalent weight. So, of course, if it is asked to you what is the epoxy equivalent weight of diglyceryl ether or bisphenol A, you should be able to find out, because you know the molecular weight and you know how many epoxy units are there. So, you can find out. And the same way you can also say what is the phenol equivalent weight of bisphenol A, principle is the same. So, you can find out by that principle. So, what we will now do is we will try to take a closer look at this particular reaction. So, the first step in this particular reaction is the base catalyzed coupling of this bisphenol A with epichlorohydrin. So, what happens here is the following. So, I am just drawing this part is some general part, and then you have the bisphenol A hydroxyl unit on this side. All right. So, this reacts with sodium hydroxide. So, this is this acts as a catalyst, and then you will have O minus Na plus, and then water that is produced. Now, this reacts with your epichlorohydrin. So, of course, this will attack on this side which is hindered, which is less hindered side, and this will open this up. So, ultimately what you will get is the following. All right. And if this is protonated, this will be protonated by water. So, what you will get is basically secondary hydroxyl unit. This is how the secondary hydroxyl unit will be generated. This is called your chlorohydrin. So, this is a basically base catalyzed coupling of bisphenol A with your epichlorohydrin to give you a chlorohydrin, and then the second step is basically a dehydrohalogenation of this intermediate with a stoichiometric amount of base. So, the first step, the base is acting as a catalyst. It is a catalytic amount because it is regenerated. You can see O minus, it takes up a proton, and then OH minus will be generated. You start with OH minus, you get back OH minus. So, that will be your catalytic amount, and in the last step it will be stoichiometric amount because it can abstract this proton here, and this O minus can attack on this side, and the chlorine will be going out. So, ultimately you will have a dehydrohalogenation with stoichiometric amount of base for the last step, and this will be your product. So, you have CH3, and then you have, so this is your product. Now, something that you should keep in mind, and something that I also told you, that what you are going to do is usually you are going to use 10:1 of epichlorohydrin to bisphenol A. High ratio of epichlorohydrin to bisphenol A has to be used in order to minimize the value of N. In other words, in order to maximize the yield of diglycidyl ether of bisphenol A. All right. And in fact, here if you are using epichlorohydrin, so your epichlorohydrin to bisphenol A, this ratio, if you are taking 10:1, then what you will have is that you will have maximum amount, it will be N equals to 0, the product will be your diglycidyl ether of bisphenol A, this N equals to 0, and this monomer will comprise, so this monomer, so the DGEBA, diglycidyl ether of bisphenol A, it will comprise more than 85% of the reaction mixture. The product will be more than 85% will be DGEBA, reaction mixture. Okay. And typically, so this is your liquid epoxy resin preparation. So, more than 85% of the reaction mixture will be your diglycidyl ether of bisphenol A, which is this molecule. So, your N value is very small. I already told N is quite close to 0.2, very small value, and 5 to 15%. So, rest of it will be higher oligomers, mostly it will be N equals to 1 or N equals to 2 compounds. So, on an average then the value of N will be very low, and that will be your liquid epoxy resin. So, to summarize what we have talked about epoxy resins until now, that this epoxide linkage is a highly strained system, and so this makes it versatile to be reacted with different curing agents under different sets of conditions, different temperatures, and so it is based on diglycidyl ether of bisphenol A, and this is your diglycidyl. So, this is your glycidyl ether linkage, and you react with your epichlorohydrin with bisphenol A in presence of sodium hydroxide to generate your final structure of epoxy resin. And depending on this ratio, if this ratio is very high, typically 10 to 1, then this N value is very small, and what you will get is a highly viscous liquid, and that will be a liquid epoxy resin. And typically your N value is close to 0, N equals to close to 0.2, 0.3 like that when you are getting your liquid epoxy resins. And we also talked about the concept of epoxy equivalent weight. So, what we will do in the next class is we will continue discussing about the preparation of epoxy resins. More so, we will start talking about the solid epoxy resins, and then we will also talk about how to cross link these different epoxy resins. So, until then, thank you, and see you in the next class.